How to test 1588 version 2 precision timing protocol. A presentation by Calnex Solutions. Hi, this is a presentation to show you how to test 1588 version 2. The assumption of this video is that you have already viewed the How 1588 version 2 Works video on calnexsol.com, or that you have an understanding of the 1588 v2 protocol and technology. If you have not viewed this video or are still new to the technology, please view the video How 1588 version 2 Works before viewing this testing video. Right, on with the show. 1588 version 2, as a reminder, is a protocol and technology that allows you to take time information from one point of the network across to multiple points in the network by the utilization of a master reference clock and slave clocks distributed through the network to recover time and align these clocks with the grandmaster, thereby achieving synchronization. Now, 1588 version 2 is a protocol that's been encapsulated under the ITU-T standards, a bunch of standards here that relate to the deployment of timing and synchronization across a packet network. There's a series of recommendations related to deployment and the distribution of frequency, and a series of standards related to the distribution of time and phase. Now, all of these standards and recommendations effectively specify the framework, the architecture, as well as the performance of both clocks and the networks themselves. Now, with these set of rules, you have the recommendations and guidelines to deploy a 1588 version 2 based network to deliver frequency and/or time and phase. Alongside these recommendations, or within these recommendations, are actually performance and therefore test guidelines, and that's what this video will cover. So first of all, we need to look at the guidelines for testing the network elements or the clocks themselves. The first element we'll be looking at is an ordinary clock, specifically how to test the performance of a slave clock. Remember, 1588 version 2 is about the slave clock recovering time from a grandmaster. So in a network, a slave clock tries to recover time from a master in the presence of packet delay variation, or PDV, caused by switches and routers in the network. This packet delay variation accumulates in the network, and slave clock recovery is therefore a challenge. Many tests have shown that slave clock recovery, particularly time and phase recovery, is a significant challenge in the presence of network PDV. So when you're testing a slave clock, you're really testing its robustness to packet delay variation and asymmetry. So how do you test the performance of a slave clock? In other words, testing its robustness to the PDV. Well, in the lab, the slave clock is really tested by using a product like the Calnex Paragon X to apply the stress of packet delay variation. There are test cases specified under the G8261 recommendation, which can be applied by the Paragon X product onto the slave, which then has to recover the clock under the presence and stress of the packet delay variation. We're testing the robustness of the slave to recover, first of all, the frequency measured by way of an E1, T1 against the relevant standards, or the time and phase, the 1 PPS and time of day against versus specified limits. We measure the recovered clock from the slave in the presence of packet delay variation. And what we're doing here is we're testing the robustness of the slave to be able to recover an accurate clock within the limit in the presence of network conditions. There are basically an extension of that initial lab test that you do is also to then test the ability of the slave to then work under real network conditions. After doing the test cases specified in the standards, you can then use the Paragon product from Calnex to capture packet delay variation profiles from real networks, including your own network, and then replay these very profiles back in the lab and measure the recovered clock from the slave. What you're doing here is you're accurately reproducing the packet delay variation conditions from your network and checking that the slave will recover the clock under these conditions. The next step of lab testing for the slave is really to characterize the slave performance under various network conditions. We talked about network packet delay variations. So these are packet delay variations that are either from the G8261 test cases or from the real network themselves. These PDV profiles can then be also represented as packet metrics. There are many packet metrics that are defined under the ITU-T recommendations. One of the key activities to do before deploying 1588 is to really determine the correct metric as well as the limits for each slave clock that's going to be used in that network. Every slave clock is going to be slightly different, or every slave clock from a different vendor is going to be different. So for each vendor of a slave clock, you need to characterize the parameters of the SLA packet metrics which relate to that particular slave clock. These limits can then be used in the network when testing in the network. So again, the process for determining the network SLA in the lab is specified by the ITU-T and also implemented using the Paragon X product. More details are available from your CalNex representative. So in the lab for testing a slave clock, first of all you test the robustness of that slave clock to packet delay variation, both the G8261 test cases as well as real network test cases. And then you characterize the limits, performance limits for that slave so that you can use these limits in the network. So that's the slave clock. Remember from the presentation, the introduction to 1588, there are also devices called boundary clocks and transparent clock. A boundary clock is fundamentally a back-to-back slave and master. Remember, the boundary clock alleviates the problem of PDV by fundamentally reducing the amount of PDV that accumulates. The PDV is really only from one node in a network of boundary clocks. The boundary clock is recovering and regenerating the clock. This is the same concept as exists in TDM or synchronous Ethernet network. And when you recover and regenerate a clock, the key testing or the performance testing you need to do is really to test the output noise, the noise transfer, and the noise tolerance of these clocks. And that is exactly the test methodology for boundary clocks. The boundary clock really needs to be tested because we need to characterize if there is noise on the ingress or the input of the clock, what effect will that have on the recovered clock? Additionally, the buffers in the boundary clocks themselves, particularly the final Q buffer, will add an element of delay and delay variation or noise. So we need to characterize the noise output from the boundary clock. We need to test the tolerance of the input to noise as well as the transfer of noise through that boundary clock. The test parameters are all being specified and drawn up as part of the ITU-T G8273.2 recommendation. And as we described before, these really characterize the output noise, the tolerance, and the transfer of noise through a boundary clock, as well as its reaction or response to a shift in clock reference. The CalNex Paragon X product can be used as a single box solution to run all of these tests for the boundary clock. The other element that can be used in a 1588 network is the transparent clock. And again, if you recall, a transparent clock helps the slave clock recover time by reporting its own delay. In a network of transparent clocks, each delay is reported into the correction field. The slave clock then corrects for the packet delay variation using the value of the correction field. But to test a transparent clock or the performance of a transparent clock is fundamentally the accuracy of the correction field. To test the transparent clock's accuracy, we measure the error in its correction field. How do we do this? Well, we fundamentally do this by comparing the actual latency of a packet through a transparent clock with the value in the correction field. Remember, a packet goes through a transparent clock. The latency time is reported by the transparent clock in its correction field. So the Paragon product from CalNex can measure the actual latency and compare it to the correction field. One of the key requirements here is the accuracy specifications for transparent clocks in some standards, for example the IEEE standard, is actually less than 50 nanoseconds. In order to measure less than 50 nanoseconds, you need a test product that is accurate to nanoseconds, which is what the CalNex Paragon X does. Once again, we measure the actual latency of the packet through the transparent clock, and we compare it to the latency reported by the TC. And here are some real results. We measure the latency, and in this test, what happened was we put some traffic and loading into the transparent clock, so the delay changed. We then plotted the correction field value. So what we're really doing is we're comparing the first graph and the second graph. The first graph is the actual latency of the packet. The second graph is the latency reported by the TC. And the difference between these two is fundamentally reported as the correction field accuracy or the correction field error. And in this real world test, in a network of 2 transparent clocks, there was an error of about 70 nanoseconds, so about 35 nanoseconds peak-to-peak error per transparent clock, which is within that limit of 50 nanoseconds. Again, the Calnex Paragon X is the only product in the world that allows you to measure transparent clock accuracy down to the level of nanoseconds. Testing the slave clocks, boundary clocks, and transparent clocks are described in detail in application notes available at calnexsol.com. Once we finish testing in the labs, we can also implement testing in 1588 in the network. Now, in order to do this, remember, we had established the network SLA parameters in the lab. We characterized what are the performance or packet metric limits for the particular slave when we did the lab test. These limits can then be implemented and used in the network itself. When we're testing and troubleshooting in a network, we would run these measurements and run the 1588 packet delay variation and metrics to compare the actual network performance against the performance limit. We can also measure the output of the slave clock. We can measure sync E, frequency, as well as 1 PPS time a day to measure all of the packet and clock measurements using the Paragon product all at the same time. So in the network, we're measuring against the SLA parameters that we established in the lab. Furthermore, if these parameters show a failure or a problem, we can use a multitude of tests to be able to troubleshoot where exactly the problem came from and what the problem is. And then longer term, we can also monitor in service. In conjunction with ADVA, the Calnex SyncDeck solution allows probes to be installed in the network and the SLA performance for 1588 and or Sync E to be monitored using a distributed monitoring system. So just to summarize again, testing 1588 is about lab testing followed by testing in the network. The lab tests are primarily governed and driven by the recommendations. There are different tests run for slave clocks, boundary clocks, and transparent clocks. All of these tests are described in great detail in the application notes available from the Calnex website. Testing can then be taken into the network, where troubleshooting tests can be done on the 1588 or synchronous Ethernet, as well as a distributed monitoring system to proactively monitor and fix problems or find problems before they happen in a deployed 1588 scenario. Once again, more information is available on our website, www.calnexsol.com. Thank you for your time today.